Today we will discuss a paper called Galore, which is a memory-efficient LLM training by using the gradient in the low-rank projection. So you can see that this is a method to do the memory efficiency training, so that we could train the LLM models in the consumer cars GPU card, which has only 24 GB of the memory. And the way we are doing, we are implementing using is using the gradient in the low rank projections. Okay, so let's review the previous method, which we call LoRa. In the LoRa, is an memory efficient training algorithm as well. In the LoRa, we will actually use to augment the weight matrix here, which is a projection matrix of a key querying and the value to a lower rank matrix. So the original weight could be augmented by a pair of low rank matrix. So during the training, we will not change the original matrix. We will actually change the low rank matrix instead, so that the memory and the memory and the computation time will be reduced. But the problem is that the normal weight matrix will not be always a low rank matrix, so that we cannot use in the LoRa for the pre-train. We can use in the LoRa to do the fine tune. So since we has pre-trained the model with the 4 rank and using a low rank matrix to fine tune the model. So let's review the gradient descent process. So in the gradient descent algorithm, we will update the weight by using the gradient and in the learning rate defined by the lambda here. And but by using the vanilla gradient descent, the converge rate will be very slow. So typically we are using the optimizer such as the momentum and the Adam, and there's a lot of optimizer here. But all those optimizer can be defined by using a sigma function, which take the gradient as the input. And then inside the gradient, inside those functions, you need some working memory to keep the history of the gradient, so that so in those algorithms we will using the history of the gradients, so that we can find the better way to update the weight matrix. So for example, in the Adam, we need to store the nt-1 and the vt-1 here, so that those are calculated in the previous steps. But actually, both n and v here will be d by d, will be in the same size as the weight matrix. So if we want to save the memory using for the working memory, using to save the history of the gradients, we hope that we can store those metrics in lower rank. So for example, if we change this from the 2048 by 2048 to 2048 by 512. So in this way, we can save 75% of the memory. But the problem is that, is the gradient really low rank? And this paper provides some proof of it, but we will skip for it for now, and we will go back to this topic later. But the intuitive is that every output will be related to some of the inputs only, since and the gradient of the input, so that the gradient of input will be related to sum of the output only. So it means that the gradient should be sparse and has high probability to be in the low rank. So this is intuitive. For the weights itself, it might not be low rank, but the gradient, since that it will work on a certain input set only, and the certain input set will using part of our weight matrix only. So we hope that the gradient will be in the low rank, and actually in practice it will be a low rank when we check the result. Okay, so the next question is that how could we get the low rank representation of the gradient? So the easiest way is using the SVD decomposition. So we could decompose the gradient to be this form by using the SVD. Okay, so in this way, the P, both P and the Q will be positive semi definite matrix. Okay, and the sigma will be a diagonal matrix, and whose the value in the diagonal item will be sorted according to the sigma and to the value. So in the left top layer, the sigma will be bigger, and in the right bottom side, the sigma will be small. So typically when we try to using SVD to convert the matrix into the lower rank, which can just set the smaller eigenvalues to be 0, so that the rank will be reduced. For example, if we just select the first 3, the rank will become the 3 by 3 from the n by n. Okay, so it means that we can using this matrix to project the GT into a lower space. So for example, we can using the PTGQ here to project it to a lower space. We can check it in the next slide. And for now, we know that this will be in the lower space, so that the Adam algorithm will actually work on less lower space only instead of in the full rank space. So after we get the result, we can project it back to the original dimensions to get the GT, which can be used to update the weights, which is in the full rank. Okay, so let's check what's going on in this formula. Okay, so for the GT, we were using the PT and the QT to project it into a lower space, and then we can using the low T here, which is should be the Adam algorithm, to calculate the weight from the heat to calculate the average value of the weight when we consider the history of gradient, and we normalize the learning rate by using the square of the gradient. Okay, so after we get this vector, so we can just using PT and QT to project it back to the original dimension, and then we get a GT here. So if we say that this is 1, so it means that okay, so we don't use in the Adam algorithm. So in this way, you can see this 2 cancel, this 2 cancel. Actually GT will be the GT. Okay, but in practice, we will not using both the PT and the QT. We are using one of them only, and one of the measure which can be projected D to a lower space. But if the GT is D by D, we can use in both sides. So in this way, we can actually using the PT rho T PT transpose GT, and we move the Q outside the Adam algorithms. So he will become the QT and the QT transpose, and this is actually 1. So actually, okay, we're using this formula to update the gradient. So we can see that in the algorithms. So in this algorithms, the Adam with Galois algorithms. So in this algorithms, initially we were using a normal backpropagation to decide the GT here. No. And then we need to decide the PT by using the SVD. Okay. And typically we will design a parameter called T here. So it means that we will keep using the same PT for the T periods. So it means that we will change the PT every T periods. So this is what this block means. So because if we do the SVD decomposition in every iterations, the overhead will be really high, and actually the performance will not be better. We can see the experiments result later. Okay, so we will choose a good the periods and according to the experiment result. And in the result, I remember that it said that we can choose any number between the 5 and 50 to the 100. During this range, the performance will be very similar. Okay, so and then we will project after we decide the PD, we will project the gradient to the lower space. Okay, so which will be RT here. So RT will be a lower rank matrix. So it means that and then after we get the RT, we can use in the RT to implement the regular Adam algorithms. Okay, so we get the NT here. But if the NT will be project back to the original dimensions by using the P matrix here. So you see that we're using a P transpose to convert the GT to the lower rank, and we're using the P to convert it back to the original rank. So this is exactly the formula we discussed here. Okay, so after we restore the NT back to the original dimensions, we can set it as a GTLT here, and we can use in the regular gradient descent to update the parameters. So that's actually for the Galois, we only modify the optimizer only. So and we optimize only by introduce the PT here by using the SVD to decide the PT, and then we implement the original algorithm in the lower range subspace. Then so that we need less computation time and less memory for it, and then we will using this gradient estimated in the lower range subspace to using this to update the weight matrix. Okay, till now I guess you can see why the Galois can have a very similar performance as a full rank matrix, because you can see that the matrix actually updated in the full rank in the original dimensions. We only estimate the gradient in the lower rank, and this estimation will be very close to the optimizer value because the gradient itself is in the low rank. Of course, according to the conclusion we give above, there is some small probability that the GT will not be a very good estimation. In that case, we might update the weight in wrong direction during the period. But since there's high probability that the gradient will be in low rank, and this will be in, for example, in 98% you will work very well. And the only overhead here is actually the SVD decomposition. This is why we hope that the T will be a bigger value, so that we don't need to introduce so many SVD here. So if, for example, if we set the T to be 1000, the SVD overhead could be ignored. But if T will be some smaller value, for example, the 50, the SVD will, according to a paper, the SVD will still take less than 10% of the computation time. So let's think about how we want to change the P here. Okay. The reason we want to change the P is that so since we are working in the lower range space, so it means that we are working on a certain subspace of the whole matrix vector space, the weight vector space. Okay, so for example, in here, by choose a P here in this point, we will actually search the planar defined by the P This blue planar is defined by the P. So we will keep update the weight matrix in this subspace. If we keep working in this space only, we will not be able to find the optimized solution, which might not be in the subspace. So to some point here, for example, let's say T, for example, is the 1000 steps. So if a T is 1000, we do the SVD again. So we get a new P. We'll get a new P here. So it means that the new P will define a new subspace. So it will be purple one here. So we will keep updating the purple one here. So since we will keep changing the subspace during the training, so we hope that eventually we can cover the full range space, the entire dimension required by the weight matrix. So that's the result in the paper. So it tells us that between the 50 and the 1000, you can see that the perplexity of the model will be the same. So you can see during the paper, if we're using the same rank, those points are almost the same. Okay, so it means that if we choose the update period between the 50 and 1000, they are the same. So it will depend on how often we hope to change the period. But you can see that if we keep doing that search in the same space for a long time, the precision will be increased. Okay, so it means that we cannot find good solutions. We need to, because we don't switch the subspace for enough times, so that those subspace will be cover the full range space. But the interesting thing is that if we would keep changing the subspace, it cannot achieve the good result as well. Okay, so even though we don't consider the overhead of the SVD, keep changing the space is still not a good idea. Actually, I don't know the real reason for it, but I believe that it might be violate some if for example, if we changing the substrate every time, it means that we don't. Let's check the formula here. Oh, it's not here. Let's So the reason that GT is in the Rosing is that we will update the T for a lot of steps, so that this one will become a small number. So if we don't really update enough steps, this all of this item will not be, none of this item will be 0. Okay, so we will go back to check that later. Okay, for now, we only need to notice that during this period, during this region, actually the performance is not very good. So we still need to have enough number of steps. So I guess before the 50 and the 1000, maybe we can choose 100 or 200. It could be a very good values. And then we can there's a comparison between the LoRa and the Galore. So in the Galore, for the weights, we need NN to store the weights. But in the LoRa, since we're using the lower range matrix to store the difference, to store the difference for the fine tune. So we need the memory for NR and the NR here with extra memory compared to the Galore. And for the optimization states in the Galore, we only need to do the storage to store the N and the V for the Eden. For here we assume that is Eden here, so we need to memory for the N and the V, so two copy of NR here. For the LoRa, we need to have two NR and two NR for the A and the B matrix here, so we need two NR and two NR here. So you can see that the LoRa will use more memory than the Galore. For the Galore, it's very simple. We only need the memory to store the MV in the lower rank. And the Galore can search in the multi-subspace, since we will keep changing the projection matrix. But in the LoRa, you won't. You just using a single lower rank matrix to store the difference due to the fine tune. But actually, we can using the multiple matrix to search for multiple subspace. Okay, so just like the Galore, every for example the T steps, and we can merge this matrix back to the original space and then generate another new low rank matrix for the next stage of the training. So in this way, we can support the subspace, multiple subspace. But in the original LoRa, we cannot do that. And the LoRa cannot be using for the pre-training, since the original matrix is not in low rank, so we cannot do that. And both of them can be using for the fine tune. So now, in this comparison, it looks like we have no reason to using the LoRa. We should always using the Galore for all the training. Of course, the Galore is a very new algorithms. We still need to see the following study to see how good it is. And comparison between the low range algorithms. In this paper, they compare to the Galore to a full rank. It means that we don't do any modification using the full rank to calculate the gradient, or we using low rank to decompose the weights into a low rank matrix. So we using only a low rank matrix, and then we discard the original matrix. So for example, we have matrix and we have a decomposition here. We have a low rank matrix here. In the low rank, we're using this one only. We'll discuss this one. And in the low rank, we're using both. Okay. So actually, the low rank here is just for comparison. You can see that the performance is actually terrible. So let's prove that actually the weight matrix is not a low rank matrix. So that if you're using a low rank approximation, the performance is actually not acceptable. Okay, and the LoRa and the ReLoRa. Okay, and in those comparisons, you can see that the Galore get the high performance in all configurations, but actually using much less memory compared to the other algorithms. Okay, and here is the experiments. They are trying to pre-train the Llama 7 billion models in the C4 database for 150,000 steps. Okay, and we will see the performance of it, and you can see that the Galore actually the performance is very similar to the 8-bit Eden in the full rank. So using a much less memory but get a very similar result. And those papers will show more details. The graph will show more details. So it means that you can see that the baseline is a full rank, and we can reduce the rank, and we don't see any big difference between those situations. So it means that by using a different, the Galore can use in a different optimizers, and they can achieve a very similar result. So in this picture, we will see the red line here. Red line is the consumer class GPU card, which has a 24 gigabyte of the memory. Okay, so the Galore is the only one which can be pre-trained and fine-tuned for the 7 billion models in the consumer class of cars. So this is amazing. We could fine-tune the Llama 7B in our computer. Of course, it will take a very long time to do that, but we can do that. At least for the memory, we will not be limited by the memory. Okay, so this is the result of this paper, and there's only one part we are missing in the paper. In the paper, it actually discuss to check if the gradient really in the low rank. And in the previous discussion, we assume that the gradient is in low rank, and but if the gradient is not in the low rank, we might update the weights to the wrong direction, because we ignore some important gradients when we project the gradient into the low rank subspace. Okay, but so in this paper, it discussed that if the network is something called reversible network, so the reversible network is defined in the other papers. So the purpose of the reversible network is that they try to propose a simpler more constrained network, so that we will be able to analyze it theoretically. So if the every operators in the network is reversible, we could call this network to be a reversible network, and the linear, redo, shortcut, and the softmax, those operators are reversible. Of course, there is some other operators using in the transformer is not reversible. So overall, the transformer is not a reversible network, but we still can we can try to using this to analyze the gradient inside this kind of a network, and if under this, because now the linear redo shortcut softmax, we can use them to compose a lot of network already. So if those network could be the gradient of those network is in low rank, so in other operators which is not reversible, it might be in the low rank as well. Now we can in the future we can do some experiments to check if the gradient is really low rank or not. For example, in the algorithm here, when we do the SVD, actually we can know that if the gradient is low rank or not by checking the eigenvalues generated by the SVD. So if for example, if we hope that the rank of the gradient will be less than 512, so that we can check the eigenvalue below the after the 512 to check if all of them are small value. So if all of them are very small values, we know that the GT is in a lower rank. So we actually cannot get the rank of the GT whenever we do the SVD decomposition, so that we can collect the data here to decide if during our training how many gradient are in lower rank or not. Actually, I don't see this number in these papers. We may try to figure out this number in the future. Okay, so we go back to the analysis here. So in this paper, in the appendix of this paper, it provides the proof that we have a series 3.2. So it says that if the network is reversible, the gradient could be represented in this way. Okay, and if this proof is much easier, so you can check the appendix by yourself. And in the next slide, we'll discuss if we know that the GT is in this form. The gradient it has high probability to be low rank. So why do we use the high probability here? Because we are actually using we are using a numerical way to estimate the rank of the matrix, so that we can only say the high probability. Okay, so if a G is this one, and we will using the GT decided by this formula to update the weights. So this is the gradient descent algorithm, and the B and the C are actually the positive semi-definite matrix. Okay, so according to the serial 3.2, so we can prove that the stable rank, which is the estimation of the rank of the gradient, will be less than this number. Okay, so before we discuss the proof, we can check why this conclusion indicate that the G is might be in the low rank. So it means that that formula tell us that, okay, so the matrix will be at least the rank 1, okay, and the lambda 1 will be the largest eigenvalue, okay, of the, and the lambda I will be other eigenvalue. So if this one will be equal to 1, so it means that the rank will be n, so this will be full rank. But if any of this item is 0, so it means that we will one less the rank. So let's check this formula. Okay, let's have a 2t here. T is the will be a big number. For example, it will be 15 to 1000. So if it's 1000, there were 2000 here. Okay, so it means that if this one is some value less than 1, you will become 0. Oh, okay. And if the lambda y is equal to the lambda 1, so it means that this will become the 1. Okay, so it means that if we have a lot of eigenvalue which will close to each other, and it will be the rank of the matrix. So if for example, if we have 10 eigenvalue which is close to each other, so the rank will be 10. And for others are small numbers, so those will become the 0. Okay. Okay, so that's why this one will prove that the GT is in lower rank, has high probability to be the lower rank. Okay. Okay, so the proof of 3.2 is that we have this one. This is by definition. And then we can substitute the WT with the WT minus 1 and the GT minus 1 here, and so it will become this one, and we can expand the second items, and so that for the first B WT minus 1 and the C here, so the B WT minus 1 C, and the A, it actually will become the GT minus 1. So this one is A minus B, this is WT minus 1, and the C. Okay, so this will be G minus 1 by definition. And the second item here, the dash lambda BG T minus 1C. Okay, that it will be here. And then since the B and the C are positive semi-definite, we could decompose them by using the eigen decomposition into this form. The DB and the DC are diagonal matrix whose value is the eigenvalue of the B. And the UT will be the eigenvector matrix. So this is a series defined in the linear algebra. Okay, so in this way we can define the HT to be the UTGV here. This is by definition. So after we do this definition, we could just substitute this line, this conclusion to here. So we can just expand it. Let's try to do it. The UT and the V, we put the UT and V in both sides, and the UT here, and the V in this side. Okay, so the UTGT minus V, Okay, by definition, it will be ht minus 1. And the second one, the utb, let's write it down, the lambda utb gt minus 1 cv. Okay, the second term will become this. Okay, and then this one and the this one, so we can substitute the b to here. So we multiply the b by the ut. So that's the ut, and so that's a cancel. So it will be this will be lambda dbut. Okay, and then the gt minus 1 and the cv product v here. So these two are cancelled. So this will cv will become the vdc. So ut gt vdc. This will be the ht minus 1 here. So the result will be ht will be equal to this one. Okay, and then we know that both the db and the dc are diagonal matrix, so that it will be easier for us to explain this one, to write the formula like this. The ht of ij will be equal to this one. You know that both of them are diagonal matrix. So only the corresponding term in the diagonal is non-zero. So for others are all zeros. So that this I and this j, for each I and j we can get one items here. So you will become this one. So that's the lambda I and the vi and the ht minus 1. Okay, according to this formula. Okay, and then we can take the ht minus 1 out, so it will become this formula. Okay, so we can see that ht will be this factor. This is not related to t, and multiplied by the t minus 1. So we can keep substitute the ht minus 1 to the ht minus 2, and then it will be the same vector here. So after we do t times of iterations, we'll get this formula, and the h will become the initial value, and the hi0ij could be the initial value of the gt here. So by using this formula to get the h0ij, so it means that the value of the h after t iterations, it will be the original one, and then multiplied by this vector. So again, if this vector this vector is the lambda 1 vj is a big value, it means that this is a smaller value, so this will become 0. So it means that for the H matrix, since the dB and the lambda and the mu will be sorted by its value, so the smaller index will have a bigger value. So it means that in those part it will be 0. So maybe in this part of matrix are all 0. Okay, so the rank of the H will be actually limited by this two sides, the smaller one of those two sides. So it means that this will be a low rank matrix. The H will actually be a low rank matrix. And if H is a low rank, it means that G is the low rank as well. And this is the other way to estimate the rank of the matrix by using a stable rank. The definition of a stable rank is this one. Okay, so and by definition we have the norm of the HT could be written in this formula. Okay, so that no, we can see that the rank will be actually limited by this formula, and we can using the stable rank to prove that the HT will be a low rank as well. But actually, we have seen this H here, since H has a lot of zero, so it must be a low rank matrix. And since the H is a low rank matrix, the G will be a low rank matrix as well. So this is the proof that the gradient is in low rank if the network is a reversible network. Okay, so but actually now in the implementation of the Galore, we don't really need loss analysis, and we can actually prove this by checking the SVD, the result as SVD here. So we can use a lot of job to test if the GT is really a low rank matrix or not. And actually, at least according to the result here, the result of the Galore is very similar to the full rank situations. So it means that the gradient should be in low rank, so that when we project the gradient into the low rank, it won't affect the performance. Okay, so this is a discussion of the Galore paper. Hopefully you will help you to understand the detail of this paper.